I'm going to continue from where I stopped last time. I was trying to prove the converse of the theorem, namely, we are assuming that, so it is this direction, that the FBI transform decays exponentially. And we took our point x naught to be 0. And so this is for x in the neighborhood of v, which contains 0, and c any direction. And to prove that, use real analytic at x naught at 0. We are going to exploit, as I said, the inversion formula. And so for that, first, let me remind you of the FBI transform, which was, say, f of tc, t and c in Rm, ei t minus y dot c minus norm of c t minus y squared u of y dy. And the inversion formula expressed u of x as the limit of as epsilon goes to 0 of this double integral x minus t dot c, the convergence factor, and then we had the norm of c to the power of m over 2 dt dc. And as I said, we are going to split this as the sum of 4 integrals, each indexed by epsilon. And the integrals will be on different regions. And so the 3 regions, the 3 of the integrals will be very easy to deal with. So let's do I1 epsilon of x, which will be the integral over the region where norm of t is less than or equal to a1 and c s sub 1, c in Rm. Now, what is s sub 1? Well, the FBI decays in the neighborhood of the origin for x. So, so that is where s sub 1 is. So we use the hypothesis. So let this decay exponentially for x, norm of x less than or equal to s sub 1. Okay, that's how you choose s sub 1. Well, in that case, look, in here, so the thing is I want to show that this will be a holomorphic function in this variable in a fixed neighborhood for all epsilon, and that as epsilon goes to 0, it will converge to a holomorphic function on that fixed neighborhood. Okay? Well, look, so this is really the crucial term. Let me estimate it. Okay, so you have f, and then you have the exponential. When you estimate the exponential, what you get is e. Well, I'm going to put x. I'm going to complexify now. So x, I'm going to replace it with x plus iy. So in that case, if you do that, the real part of this will be what? Iy minus y dot c. Okay? So e minus y dot c. And this is harmless. And this will be harmless also because I'm going to get an exponential decay as I will show. So this is dominated by this. So let me forget this constant. So you have this coming from the FBI. And this, well, this is no more than norm of y, norm of c. Okay? And you have this. Now look. So if y is very small, say if I take absolute y, say less than or equal to c2 over 2, then this gives me an exponential decay, e minus c2 over 2 norm of c, and a polynomial multiplied by an exponential decay is an exponential decay. Okay, so maybe make this c2 over 4, and then you can get rid of this. So in other words, when x is complexified in this fixed neighborhood, as a function of epsilon, this whole integrand is dominated by an integrable majorant. Okay, so independent of epsilon, and you know it's a c variable we have to worry about because in T you are on a compact set, And therefore, these guys converge uniformly to a holomorphic function, okay? Because there is a fixed measurand, okay? So therefore, I1 epsilon of z converges to some function, let me call it I1 of z, holomorphic on some disk. All right. And I2 also is going to be, I2 is also going to be very easy because I2 of x, well, I didn't tell you what the region of integration is, but it's going to be a compact set in T and also in C. For now, it doesn't matter what these numbers are, but I will specify them later on. A1 has already been specified. Well, look, if T and C are in a compact set, you know, you can put any z in here. It is integrable. It will have an integrable measurand as epsilon goes to 0. So in fact, this gives you an entire function as epsilon goes to 0, an entire function on all of Cn. Okay? That's trivia. Okay, so I2 of x, this goes to I2, well, let me say z, goes to I2 of z, which is an entire function. Let us look at I3. So this is the integral over t bigger than or equal to a2 and c in Rm. Now let me tell you what a2 is. I really would appreciate it if you guys stop communicating because I get really distracted. The slightest sound distracts me, okay? All right. So I'm going to tell you what a2 is. So remember, U is of compact support. So assume U is supported in the set X where absolute X is less than or equal to A2 over 4. Okay, so that's what A2 is. S2 is. Okay, now you see, so let me look at the integrand. Let me look at the FBI. Okay, so I'm looking at the FBI in a region where the t variable, the t is bigger than or equal to a sub 2, whereas the y is less than or equal to a2 over 4. Okay, so in this integral, so in f of t c, on the one hand, you have this is bigger than or equal to a2. On the other hand, this is less than or equal to a2 over 4. And so therefore, what can we say about norm of t minus y? Well, this is always bigger than or equal to this minus this. And I split the t into two parts, t over 2 over minus y. And so it's bigger than or equal to norm of t over 2. Now, norm of t over 2 is bigger than a2 over 4. A2 over 2, while this is less than or equal to a2 over 4. Therefore, from this, I get plus a2 over 4. Okay? And so therefore, the norm of t minus y squared itself. So therefore, norm of t minus y squared is bigger than or equal to the square of this, and I just need the square of this plus the square of this. Norm of t squared over 4 plus a2 squared over 16. And so in this integral then, you see this part now is dominated by e to the minus norm of t squared over 4, e to the minus a2 squared over 16 norm of c. So the exponential decay in t gives me integrability in t in this integral, okay? And this will allow me to complexify x in a fixed neighborhood of 0 and get uniformly an integrable measurand. So it's similar to what I did before, okay? So therefore, the whole thing will converge to something that's holomorphic again in a fixed neighborhood of the origin, okay? So therefore, the details, as I said, I'm going to leave these notes to Professor Florian, and so you'll get them from him. Okay? So therefore, I3 epsilon of z converges to I3 of z, holomorphic on the less than or equal to, let's say, R prime. All right. Now, the tricky part is last integral. The last integral is a little tricky. So, oh, wow. Why did I do that? So, what is this? E norm of C x minus, no. Is that what it is? Norm of C to the m over 2 dt dc, I guess. Okay. No, there is no. The convergence factor minus epsilon norm of C squared. All right. So in the last integral, the integration will be over the region where t is in a bounded set. I already told you what A1 and A2 are. And C is unbounded, bigger than or equal to a number B. Okay, now this time what we do is we are going to deform contour of integration in the C variable. But one has to be a little careful because while this is entire in C, in zeta, this is, yesterday I showed you, this has a holomorphic extension in this double cone. So this is C, the real axis, away from the origin. It extends in a cone like this. Okay. So if I complexify to zeta, it extends in the set where the norm of the real part is bigger than the norm of the imaginary part, which is exactly this kind of set. Okay? So I will deform contour in the C integration. So from integration over here to integration over some set in here. Okay? And the deformation has the following form. So deform C integration into the following kind of path, zeta of C equal to C plus is. S is going to be a small number, norm of C x minus y. So this is for C different from 0. The y is, the y, remember, is, oh, is there any y here? Oh, I just realized I wrote the inversion formula wrong. This was, sorry, this was, okay, yeah. So if you open up the FBI, so the integral actually is the following. EI x minus IY dot C minus norm of C t minus y squared minus epsilon norm of C squared. And then there's norm of C to the m over 2, u of y, dy dt. It's a triple integral now because I opened up the FBI, transformed the f of t. Okay? And so it is in the C integration that I'm going to deform contour. So C gets replaced by zeta of C. And so the whole thing, after I replace it with zeta of C, I will have, so I for epsilon of x over the region where I'm integrating. So I will have something like e to the power of an expression, which I will call xytc. And this has this holomorphic extension. Okay, I denote it by this, to the power of m over 2, and then u of y dy dt, and then there is a Jacobian factor. Okay. Now, so the crucial term to estimate, again, is going to be this exponential. So I have to look at the real part of p. Okay? So write out what p is, and basically what you'll get is the following, that e to the p will be less than or equal to e to the minus s. S is to be chosen. Well, S, you choose it small enough so that when you deform contour, you are inside here, okay? The point is y is in the support of u, is bounded. X is going to vary near 0, so this is bounded. And so if S is small enough, certainly norm of this will be bigger than norm of this, which is exactly what this set is, okay? All right. So minus t minus y squared over 2 norm of c minus epsilon norm of c squared. So again, I just have to show that. Remember, the t, in this region, t is bigger than or equal to, what was it, a sub 1. Okay. I have to show that this has an integrable majorant. Okay. In y, there is no problem. U is supported on a compact set. So now look, the y, what was the y? In the support of u, so y is less than or equal to this. So take two cases. Case 1, say y is not close to t, which means say norm of y is less than or equal to a1 over 2, say. Okay? Well, since norm of t is bigger than or equal to a1, then t minus y squared will be bigger than or equal to some positive number. And so you get your exponential decay from here. This is harmless. S is going to be taken positive, okay? Okay, case 2, if norm of y is bigger than or equal to a1 over 2, then in that case, there is a risk that y might get too close to t, which means this will not contribute anything. But x, I'm interested in x near 0. So take norm of x less than or equal to a1 over 4. So this will give you the decay you want. This is harmless. Okay? So in both cases, you'll get the appropriate exponential decay and hence majorant, an integrable majorant. And so again, you can let epsilon go to 0. And for z near 0, you get holomorphic function. Okay? And that finishes the proof. Okay? So as you can see, the converse direction needed some more work. Okay. Now we will get into some more interesting stuff, hopefully. First, about Taylor series. Taylor series of a smooth function. Okay. My goal is to show you, remember yesterday I said a smooth function in real space X in Rm can be characterized as being the restriction of a function which is d bar flat in X space. So that is my goal, is to prove that. For that, we need some preparation. So first, classical lemma, it's called Borel's lemma. It's about Taylor series, Borel's lemma. Namely, suppose I give you a sequence of numbers. Let A alpha be, these are complex numbers. So alpha here is an index, z to the m or z to the n. Okay, I guess we are working in Rm throughout. And I ask you, this is the problem. Find a function f, a C-infinity function on all of Rm, such that its Taylor series at 0. So the Taylor series coefficients, it's not divided by 2. This is exactly A sub alpha for all alpha. Okay? This is a nice calculus problem, right? You want given a sequence. So it turns out there is. The thing is, you see, if a function is real analytic, then the Taylor coefficients have to grow in a certain fashion that I mentioned yesterday. But if it is smooth, you can't say anything about the Taylor coefficients. They can grow in an arbitrary manner. They can come from an arbitrary collection. That's what this is saying, okay? So, but the thing is, how do you construct a smooth function whose Taylor series is given by this, okay? Well, the first attempt, of course, the first thing is, so you want to try, well, what does the Taylor series look like? It's going to look like this. I mean, this has to be the Taylor series so that this is satisfied, right? Except, of course, there is a problem, right? That you don't know if this converges, okay? So, in general, this diverges, okay? And so what I'm going to do is I'm going to multiply each term by a function whose support gets smaller and smaller as alpha increases. Okay, more precisely, you take a smooth function of compact support, let chi be a C-infinity function of compact support, such that chi is identically saying 1 when norm of x is less than or equal to half, and chi is 0 once you are outside the unit disk size. Okay? So very simple cutoff function. This is your chi. And then I'm going to take an increasing sequence of numbers which are going to be determined. Let 1 be less than r sub 1, r sub 2, r sub 3, and so on. And now here is what I propose. So let f of x be equal to a alpha chi r to the alpha x, x to the alpha, alpha. Now, the r's are going to be chosen in such a way that, for example, they will dominate the a alpha. So they will be chosen in such a way that this will be convergent absolutely on order of Rn, okay? All right. So how do we choose the A alpha, okay? How do we, okay, so roughly, so far, you see, these functions now are supported in this less than or equal to this, because chi is supported in the unit ball. And so you see, as alpha increases, the support of these functions is getting smaller and smaller. It's getting smaller and smaller. But in the neighborhood of 0, each of them, well, or for each of them, there is a neighborhood of 0 where they are constantly 1. And therefore, this will be the Taylor coefficients at 0, okay, at 0. Okay, so what I'm going to choose to show you is that I can choose the R sub j such that not only does this converge uniformly, but all order derivatives will also converge uniformly on all of Rn. Okay? Now, if I show that the series of derivatives converge, then that means that f is going to be C infinity. Okay? So this is a calculus factor. Okay? So let's start with continuity first, the simplest thing. Let's first show that this series will converge with the appropriate choice of the R alpha. Okay? So continuity, step 1. Well, let me estimate this, guys. So I have A alpha chi R alpha x, x to the alpha. Okay? Now, this is 0 unless this is satisfied. And therefore, the x is dominated by 1 over r to the alpha. And the chi, I could have assumed here, I could have chosen so that chi is always less than 1, okay, and negative. Is that clear? So the first thing to choose then is to make sure that r absolute alpha is bigger than a alpha. Okay, so choose. That means choose r sub j such that r sub j is bigger than a sub alpha for all multi-indices whose length equals j. Okay? Well, in that case, this will be less than or equal to 1 over r to the alpha to the power of alpha minus 1. Now, if this series converges, the Weierstrass M test tells us that this will be a continuous function, right? That's what Weierstrass M test, okay? And so, well, this is less than, and you choose these numbers so that they are increasing. So this will be less than or equal to 1 over r1 alpha minus 1. r1 is bigger than 1, therefore the series converges, okay? So Weierstrass, so since r1 is bigger than 1, this series alpha in Zm converges. So by the Weierstrass M test, f is continuous. Okay? We're done with continuity. So now let's look at derivatives. I take a beta, a multi-index, and I look at the beta derivative of this. Well, I'll look at the series of the beta derivatives and show that that converges, provided that I choose this appropriately. So far there is only one condition really on the RJ, or two conditions. They should be increasing also. So now more conditions will come. So let beta equal to beta 1, beta n, be fixed multi-index, m is what I'm using, fixed multi-index, and take the beta's derivative of these terms, a alpha, chi of r alpha x, x to the alpha. Okay? So Leibniz rule, okay? The product rule. Okay? What does the product rule say? Well, a alpha comes out, and so I have to integrate over all gamma multi-indices less than or equal to beta. Multi-indices gamma less than or equal to beta means each component-wise, gamma j is less than or equal to beta j. Okay? Gamma, and then, you know, if I were, this is what I do. I first do it in one variable. Okay? I do it in one variable. You know, if I don't do it in one variable, then I'm hopeless. I do it in one variable, try to understand it very well then, and then go to multi-variables, okay? So when you differentiate the product, what do you get? You get the beta minus gamma derivative of chi of r alpha x times the gamma derivative of x to the alpha. And here you have beta gamma. And notice, when you differentiate this monomial, if gamma j is bigger than alpha sub j, you are going to get 0. And therefore, gamma is also has to be only gamma less than or equal to alpha matters. Okay? All right. Now, this I write as, therefore, gamma less than or equal to beta alpha, beta gamma. And then when you differentiate this, I get the beta minus gamma derivative of chi, evaluated at r alpha x, times r to the alpha with beta minus gamma power coming out. When you differentiate this gamma derivative of alpha, what do you get? You get alpha factorial over alpha minus gamma factorial, x to the power of alpha minus gamma. Again, do it in one variable first, and then you'll see it in higher variables. Okay? All right, so there are these new quantities that are coming. You see, before, when I checked continuity, it was only the size of chi that came in. Now it is the size of these derivatives. So, so in brackets, well, chi is of compact support, so these are bounded. So let's d beta minus gamma chi in general. So let this be less than or equal to constant I call m beta minus gamma. Okay? And then what I do is choose the Rj such that m sub anything, say m gamma prime is less than or equal to Rj whenever the size of gamma prime is j. Okay? So this is an additional condition now on the Rj. And that's about it. I don't need any other condition. I'll show you this series converges uniformly on Rm. It will be very easy. All right, so where are we? So this gets replaced by this number. And x, remember, all this matters only if this is not 0. So norm of x is less than 1 over r to the alpha. So I get 1 over r to the alpha to this power. So let me put absolute value. So the absolute value of the beta's derivative of a alpha, chi of r alpha x, x to the alpha, ends up being dominated by, there is absolute a alpha. Remember, a alpha was dominated by r to the alpha. That we already have. The sum over all beta less than or equal to gamma alpha. Oh, no, gamma less than or equal to beta alpha. Gamma less than or equal to beta alpha. And then I have, so I have beta choose gamma. So for the derivative of chi, I have m beta minus gamma. And then I have r to the alpha beta minus gamma power. And then I have alpha factorial alpha minus gamma factorial. And x, remember, is dominated by 1 over r to the alpha. What is the power there? Alpha minus gamma. Okay. Now look at this term and this term. The minus gammas will cancel out, so it will give me r to the alpha. Well, I'll get r to the alpha to the power of beta. There is an r to the alpha here, so I add that. Otherwise, at the bottom, I have this. This is good because I'm summing up over alpha. Beta is a fixed thing, so this is not going to matter. Okay, m beta minus gamma is dominated by r beta minus gamma. Okay, so I have r beta minus gamma from the way we are going to choose the rj. And so I have this. What did I leave? There is alpha factorial over alpha minus gamma factorial. Now, the thing is that you are differentiating with respect to beta. When you differentiate with respect to beta, the series, when you differentiate with respect to beta, see, you are differentiating this, a alpha, blah, 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 okay, x to the alpha. The first finite number of terms, of course, I mean, they are finite, they're derivative, that will be fine. So you may assume the alpha is bigger than norm of beta. You can assume that, okay? Is that clear? That's the only part you have to make sure converges, okay? So may I assume that alpha is bigger than beta, and that therefore, you see, this will be less than absolute alpha, okay, because the r's are increasing, so this is dominated, this part, therefore, is less than or equal to r to the alpha, so I can put it together, or I can compare it with this, okay, so I get less than or equal to, so I have beta gamma, alpha factorial, alpha minus gamma factorial. Oh, I have r to the alpha beta plus 1. And then this new additional term, so r to the alpha, alpha minus 1. And this was where? Over gamma less than or equal to beta alpha. All right. Now in here I have beta factorial on top. Let me factor it out. At the bottom, I have beta minus gamma factorial. Leave that out. You get a bigger quantity times gamma factorial. Keep that. I have alpha factorial, alpha minus gamma factorial. And I have this. And this is really a nice term. Because this is finite. It's harmless. So what I have is what? Alpha minus beta minus 2. It's harmless. OK. Now, this is over all gamma less than or equal to beta and alpha. Well, if I do just less than or equal to alpha, I get a bigger quantity. And what is this? So this has no gamma in it. It factors out. And what is this? You see, this sum, it's a simple sum. Maybe you can tell me. Maybe you have seen it. What is the sum of, in other words, this is alpha, choose gamma, right? What is the sum of that for gamma less than or equal to alpha? Do you know it? Let's do it in one variable. What is the sum of nk, n choose k for k less than or equal to n? 2 to the power of n, because this is the same as 1 plus 1 to the n, right? 2 to the n. Well, here you are doing it in each component twice, so you get 2 to the power of alpha. Okay? And therefore, this whole thing is less than or equal to then beta factorial. 2 to the alpha, well, then the 2 has to come in here then. So you have 2 to the alpha over r to the alpha. Well, one more condition on r then. You have to make sure the r to the j are bigger than 2. Okay? But then this series will converge. Okay? The series will converge, so all the series of beta derivatives converge, therefore f is infinity. All right. Now, f is infinity, but the question is, does it solve our problem? Is the alpha's derivative of f at 0 divided by alpha factorial equal to A alpha. Well, that is easy. So let me leave that as an exercise. I'll show you the one variable case, and I'll leave the general case to you. Okay, exercise. Show that. So first we have concluded that f is infinity, that series. Show that the alpha's derivative of f at 0 over alpha factorial is indeed A sub alpha for all alpha. Okay, so it's telling you that the Taylor series tells you nothing about a function, about a smooth function. Okay, of course you know smooth functions whose Taylor series are 0, right? But are non-zero, right? Like e to the minus 1 over norm of x squared, that kind of example. Okay, these pens are giving me a problem again. Yeah, I pressed. A new brand? Yeah. Is it from France? No, thank you. Okay, new brand. Okay. So show that. So let me show you the one variable case. Okay, and then just imitate that. So what we have is what was it? Aj chi rj x, x to the j. The rj's were chosen, so that this is a smooth function. So I want to show that the k's derivative of f at 0 over k factorial is A sub k. Very easy. Very easy. Let me show you why. So show this for all k. What you do is you break up the sum into two parts. See, you break this up into two parts. For each k, write it as this, rj x, x to the j, j from 0 to k, and the rest has a power of x which is at least k plus 1. Remember, although the rj are increasing, making the support of this smaller and smaller, nevertheless, it's still true that these functions are 1 near 0. And so there is since there are only a finite number of them, these functions are all 1 on a fixed neighborhood of 0. And therefore, this is 1. And this is a polynomial ajx to the j, and of course, the k's derivative of this part at 0 over k factorial is A sub k. That's trivial. This part, remember, we were able to differentiate, to interchange summation and differentiation. So differentiate, but this has at least k plus 1, x k plus 1. So if you differentiate k times, evaluate at 0, you are going to get 0. Okay? So do it also for several variables following these arguments. Okay? Is that clear? Before I proceed, any question? Okay, I did Borel's lemma. Now I'm going to give you an exercise, which is a generalization of Borel's lemma. Here is the exercise. Suppose now, instead of, in Borel's lemma, I gave you numbers, a sequence of numbers, and then I took a sequence of numbers and showed there is a smooth function whose Taylor series is given by those numbers. Now, instead of numbers, I'm going to take functions. So smooth functions. Let f0 of x, well, not f0, let f sub alpha of x. They are indexed by multi-indices. Let f alpha of x, so these are multi-indices, be C infinity on Rm. No relationships between each other. These are arbitrary smooth functions. I want to do a generalization of Borel's lemma. What does that mean? This time I want, so I want a function of xy, where here xy are in Rm cross Rm. Okay, so x variable, y variable. So you see, so I think of it like this. Here is x, here is y. I want a function whose beta derivative in the x variable at x0 is prescribed by these functions. It's kind of Borel's lemma, right? It's a more sophisticated version, okay, of Borel's lemma. The proof will be exactly the way I showed you. Okay, so here is what would work. Okay, so proof. So I'll give you the the main hint. What you should try is a function, just like in Borel's lemma. Well, if you want this to be this kind of theorem, I meant the y, the y derivative, what in PDEs one calls Cauchy data, okay, on X space. So what you should try is something like this. So the beta's derivative is supposed to be this. So f beta of x, y to the beta, over all beta. Well, of course, this is not going to converge, and so you put convergence factor. The same chi, r to the beta, y to the beta. This will work, so your exercise will be to choose the r sub j appropriately, okay? So you see, so this time, remember, you want to show this is infinity in x and y. So you have to look at x derivative, y derivative of this series and show it converges. It won't be a problem at all. So when you take x derivatives, you are taking the x derivatives of this, so the rj's will have to control those. When you take y derivatives, the same as before, the y derivative of the chi. Now, try to do it for x, y in a compact set, in a ball, okay? If you do that there already, that will be fine. Then in general, you cover all of space by this sequence of balls, okay? And the rj, you can, you'll be able to choose also. Okay, the rj will be up to a certain compact set, radius j, say, for example, and so on. Okay? But try to do it first on a fixed compact set. Okay? But this is believable in light of what I showed you in Borel's lemma. Any question? Yes?
So if I want this f to be an analytic,
huh?
if I want this f to be an analytic function.
If we want what?
This f, whatever we are constructing.
This capital F?
No, this f is now getting as a C infinity function, right?
Yes. In the Borel's lemma, you mean?
Yes.
Yeah.
If I want it as an analytic function, what should be the
Oh, no. Analytic functions, A alpha cannot be arbitrary.
Yeah, that's what
Well, the condition is, well, the alphas are supposed to be derivatives at a point, right? The condition is that the A alpha should grow precisely. There should be a constant C such that the A alpha satisfies this. Okay? This you already see in the Cauchy integral formula, actually. Now, let me show you why this is the right condition. You see, because you want this to converge, okay? Converge somewhere. Well, if the A alpha are like this, okay, and the x, basically, if it is less than 1 over c, something like that, then it will converge, okay? So the larger the c, the worse these numbers are, the smaller the set where you get the function to be analytic, okay? So that's the condition. Any other question? So now I'm going to talk about almost analytic extension. This is really all we needed. We have done the main part. So what does almost analytic mean? So first, some notations. So given a smooth function, I want to find an extension, capital F of xy, but with the property that it's d bar of f, when y is 0 to infinite order, meaning it's 0 and all its derivatives are 0. And you'll see that this kind of thing will be useful when I try to replace this idea of deforming contour for holomorphic functions or analytic functions by using Stokes' theorem for general smooth functions or C1 functions. Okay, let me make sure that I'm kind of organized, so make sure I know what I'm doing. Okay, so we have this notation. So you have f from Rn, let me use Rn now, into C. So this is x variable y. So you can think of this also as Cn, in which case the variable will be z equal to x plus iy. Okay? All right. And so you have the Cauchy-Riemann operators. df dzj bar is 1/2 df by dxj plus I df by dyj and df by dzj will be the conjugates of this, right? And you know how to, why this notation makes sense, you know, because if you write the differential of a function, what is it? The differential of a function is this one form, right? j1 to n plus partial f with respect to yj, dyj, 1 to n. Then you can write dxj, dyj in terms of dzj and dzj bar, expand this, and you are able to write the whole thing as a linear combination of dzj bar and a linear combination of dzj. Okay, where this will be made up of these functions, and this will also be made up of these functions. If you compute, if you finish the calculation, what you will see is the coefficient of dzj bar will be exactly this. Well, if the coefficient of dxj is called df by dxj, if the coefficient of dyj is called df by dyj, it makes perfect sense to call the coefficient of dzj bar df by dzj bar. Likewise here, it makes sense to call the coefficient of this df by dzj, okay? So that in terms of, you know, justifying the notation, okay? All right, now, here is, so we say a function, so f of x, vanishes to infinite order, at a given point, say at 0, if for every number n there exists a constant Cn such that f of x is less than or equal to Cn absolute x to the n. Okay? Actually, let me modify this. This is a bit too strong. In practice, what you really need is the following. If for every r positive and say n, there is n such as this is satisfied for x, because you are really interested at in what's happening near 0. Okay? So f of 0 clearly is going to be 0. Okay? And it's telling us the rate at which f of x is going to 0. Now, of course, the function may not be differentiable at all. And this can still make sense. Okay. Now, but if f happens to be infinity, then it's easy to see from the Taylor series approximation, you know, with the Taylor error, blah, blah. Then f vanishes to infinite order at 0 if and only if all derivatives of f are 0 at alpha. Okay? Yes? No, given fixed r positive and n, there is, oh, you mean here? Oh, yeah. Oh, yeah. Okay, sure. Yeah. Yeah, this is what it, yeah, you are right. Yeah. All right. Now, let me give you an example of, for example, a function which vanishes to infinite order, but may not even be, say, C1. Suppose I take sine of e to the 2 over x squared, e to the minus 1 over x squared. Okay? This vanishes to infinite order at the origin because this is bounded by 1 and this decays even exponentially. But if I differentiate, cosine comes out. And then this comes out, and this will overpower this. So already the first derivative will not exist. Okay? Okay? All right. So this notion is good when you are dealing with continuous functions. And if you want, you know, to still talk about vanishing at a prescribed order. Okay? All right. Now, let me generalize this definition a little bit. We say a function, say, g of xy, vanishes to infinite order at y equal to 0. It's really the same. If g of xy, the same kind of thing, on compact sets, blah, blah, c n r, y to the n. Okay? So we are interested in what's happening when... No. Yeah, just as before, for given a number R on compact subsets.
For the indirect, okay, but
On compact sets in X. For X and Y in a compact set.
okay.
For X and Y, yeah. That's why I have this, okay? Yeah.
But for X also.
For X also, yeah. For X, Y in a compact set, okay? And you are going to be, you see, these questions we are studying are local, so you are going to be interested always in what happens in a compact set, okay? So let me tell you now the following, which is really a very useful tool. So lemma 5, a function f, let f be continuous on Rm, then f is infinity if and only if there is a capital F of xy, which is just C1, okay, on Rm cross Rm, such that 1 at y equal to 0, it is f of x. And 2, it's d bar. D bar means df by dzj at xy. This vanishes to infinite order at 0, in this sense. This makes sense. You see, f is C1, I differentiated only once. Okay? This vanishes to infinite order at 0. One of the nice things about this is that you are characterizing a smooth function in terms of a C1 function. Okay? But the thing is, you see, this d by dzj bar, it's an elliptic system. Elliptic operators, they put very stringent conditions on a function. I'm going to show you how to apply this to PDEs, okay, complex vector fields, to get some regularity, basic regularity, okay? So that will be towards the end, okay? And that's the main goal of this whole thing, this mini course. But, and I'll show you how this is going to be useful in trying to replace deformation of contour for holomorphic functions to deformation of contour for smooth objects using this function, capital F. Now, so as you can see, this capital F is kind of behaving like a holomorphic function, analytic function. Therefore, this capital F is called an almost analytic extension of F. Of course, little f may not have an analytic extension, f may not be analytic, but it has this kind of extension, and that's called almost analytic, okay? So f is called an almost analytic extension. We really have done the hard work for this, so this will be very easy to prove, okay? We'll do it next time. But let me just say the following. It's not unique. It's far from unique. Why? We can't expect it to be unique. Why is it not unique? It's not unique because the Borel lemma, go back to the Borel lemma, the Taylor series does not tell you what a function is. And you'll see that the way we prove this is going to be using this exercise. You see, we have to construct this capital F. The fact that this vanishes to infinite order, I will show you, precisely means that these derivatives are prescribed, are given to you in terms of the derivatives of f. And by this exercise, you can construct such a capital F. Okay? Is that it? I said Anaram because I was warned I had to finish 5 minutes in advance so you can go to lunch. Stop. So you can ask questions now.